Well, welcome back to the Dragonfly Daily. I am your host, Mike Marsh, the product manager at ORS, and you can follow me at Dragonfly Wizard at Twitter. Be sure to look for me on LinkedIn and ResearchGate, but please pay close attention to orss.ca/YTP2. That is the playlist on YouTube for all of the Dragonfly Daily. While there, hit the subscribe button. In fact, if you're watching this episode live on YouTube, or I should say watching it recorded on YouTube, hit the subscribe button now so that you'll be notified of future video content that's made available from the rest of the team at ORS. Today's lesson, lesson 39, is on cylinder coordinate transforms. We're going to look at data which we normally think of in a rectangular coordinate system, and we're going to talk about cylinder coordinate systems and how you can extract data that way. And we are using Dragonfly 2020.1 Release Candidate 2. I'm going to pop over to Dragonfly and I'm going to open up my project organizer where I have a data set. This is the dry sand pack. I'm going to drag that into my workspace. Now I'm going to go over to a web browser. For those of you that may be watching these videos out of order, this is a data set we have used before. You can go over to digitalrocksportal.org and do browse published projects. If you scroll down or if you do a search for hydrate, because this is a hydrate bearing sand, you'll find this project right here. I want to take a minute here and thank everyone in science who shares data. This is tremendously helpful for the rest of the community that want to reproduce experiments and even just test out new ideas and new methods. So I want to thank Masha Pradanovic, who is the host of this data repository, as well as all of the repositories that are hosted worldwide, such as Morphosource and Digimorph, etc. So I want to thank everyone. And if you want to do the exercise today and you want a cylindrical data set, there are numerous cylindrical data sets here at the Digital Rocks portal, including this hydrate bearing sand. I'm using the dry sand pack saturated with air, which is this collection of TIFF files. Now if I pop over to Dragonfly, the data set is loaded. I can close the organizer. So it looks like this. And what we're interested in today is inspecting the data not slice-wise on the axial slices, not slice-wise on these longitudinal slices, but instead looking at the data from a cylinder perspective. So the metaphor I use here is the soup can unwrapper. So imagine that this was a soup can and you had a soup can wrapper going around the outside. If I were to cut along the seam of the wrapper and I took the wrapper off and I lay it flat on the table, I would now have a rectangular image that is the pixels that you see around the edge of the sample. So maybe you want to inspect the surface of your object, or maybe you want to inspect the object at the subsurface at some lower radius. Well, that's what we're going to look at today, is doing that transform from the cylinder coordinate system to a rectangular coordinate system. Now, to do this, you'll need an image data set and you'll need a cylinder. And what I'm describing today is not part of Dragonfly that ships. What I am describing today is a extension, specifically a custom menu item that anybody can grab from the Infinite Toolbox. I'll show you where to grab it here in just a moment. Now, when I have this extension plugged in, I can create a cylinder of any height and any diameter, and I can set those parameters interactively. Then I can come over and I can select the image and I can control click and select the cylinder. Now I can right click and I can say execute macro extract soup can wrapper. Now this is done in Python. You're going to see the source code is completely available. It's not especially fast because it's done in Python. Sometime this summer we'll actually port the Python code to compiled C++, which should give us about a 100 times performance gain. And this is what we see. This is that cylinder that I had modeled with this cylinder, and it's unwrapped. And so we can see what the pixels look like where they intersect that cylinder object. Now, if I come back and I look at my image again, I could select the cylinder and maybe select a bigger radius, and I could repeat. So if I control click, right click, execute macro, extract soup can wrapper, and I wait, then I will see the results. All right, so what we have here are two different images. This is one image, and here is the other image. Now, the way these are positioned in the world coordinate system is a little bit nonsense because these don't actually have a proper place to go in the world coordinate system. As a flat image, where should it be with respect to the initial cylinder? So you see here it's just kind of on top at some origin. I think it's actually at the 0, 0, 0 origin. These two slices are actually superimposed. They have exactly the same origin in X and Y and Z. And so they're sitting on top of each other. Now, what I wanted to do was I wanted to run this analysis for a cylinder, but then I wanted to repeat the analysis at a higher radius and higher radius and higher radius, so that I could then look at how the data change as you extend the radius. So I wrote a macro with Macro Builder that would call the menu item that we just did, and then change the radius and call the menu item again and change the radius. And each time after I make the image, I actually apply a linear, I shouldn't say a linear, I apply a displacement. So instead of having the images superimposed, I take the second image and I displace it in Y and then in Z and then in Y to line it up. So you'll see that I have this new macro that calls it multiple times, and you'll see the output of that here in just a moment. Let's do this. Let's take our two results. I'm going to group select them with a control click, and I'm going to delete them. Now, what I'm going to do is I'm going to go to Utilities, Macro Player, and here I'm going to select the Soup Can Wrapper over Radius Range. This is a macro that I built with Macro Builder. I'll show it to you in just a moment. And if I select both of these and I execute play, it's going to take the existing cylinder, which has a center position, and it's going to prompt me for a radius. Now, the radius actually is expressed in meters because I didn't pay close attention and try and convert units. So this is saying I can start with a radius of 1 millimeter. I'll click OK and proceed to a higher radius. I'm just going to set, let's say, 1.5 millimeters and click OK. And then it's going to do a step size. Now this is just happens to be initialized to the step size or the pixel size here. Now if I click OK, what's going to happen is it's going to run an extraction at 1 millimeter, and then it's going to make the radius 28 microns higher, and then higher, and then higher, and it's going to iterate until it goes all the way to 1.5 millimeters. So each of these extractions is taking, I don't know, 5 to 15 seconds, and that's depending on how tall the cylinder is and how high the radius is. So we're going to wait for that to play out, and we're going to see the results in the workspace. All right, it's done. I can close my macro player now. Now, if I close all of these images, if I close these images and then I turn on the visibility of these images, you can see what has been built up is a number of two-dimensional images in my workspace. And let's get the visibility on for all of them. Now, each of these is one slice thick, so I can't actually slice through them. Now, if I happen to select all of them, and this is just kind of a hack, if you will, if I select all of them and create a box, if I select the box, and now with the box selected, I'm going to lock the box. The reason I selected the box is the box has spatial extent over all of these, so if I come over here, now I can scroll these slices up and down, and you can see what it looks like over here at low radius, or I can grab this and drag down to high radius. So now I have interrogated, and this slice number here is not actually inspecting slices of a 3D data set. This is really a representation of the different radiuses. Now, I could select all of these images, and I can right-click and say, wait, let me make sure I selected them all. One and shift click. If I select them all, I could say stitch 3D, and this is going to create a 3D image with all of these 2D images merged. And we looked at this a very, very long time ago, and when images have overlap, you might want to compute mean or no blending or weighted, but here, because there's no overlap, at every pixel, I can just take the maximum intensity of all of the signals. So basically, I can leave max and nearest, or I could even choose tricubic, and I could just hit stitch, and it's going to put all of these in one three-dimensional image. So now I can delete all of this and select it all, delete it, waiting for Dragonfly to clean up all of those objects. Now if I select this, here is my data set over different radii. Now let's have a look at the code that we used for all of this. So I'm going to go to Utilities, and I'm going to go to Macro Player, and let's see. We can go to Macro Player. Actually, I'm going to go to Macro Builder under Utilities. We'll wait a moment for that to launch, and then I'm going to open up the extension. Let's see. Open up the specific macro I built for applying over a radius range. I'm going to zoom out a little bit. Basically, what happens in this macro is I identify if the user has a selected channel. So was there a channel selected when the macro was launched? Was there a cylinder selected? Then it identifies those. Then it prompts the user for a lower radius. It prompts the user for an upper radius, then a step size. With that done, it now executes this for loop where it, in each case, runs the menu item to extract cylinder from in this case, it's called a structured grid, but to extract the cylinder. Then I do some bookkeeping. I inspect the pixel size and the width of the images so I can do the proper displacement of the images laterally and in Z. And then I publish all of the images. So all of that's spelled out here. Now this is in the Infinite Toolbox. So if you were to go to Utilities, Infinite Toolbox. Now let's take a moment to load too. Sort of loading up these web browser toolkits in Dragonfly takes a moment. So this is my Infinite Toolbox. I'm logged in as Marsh. If I go to macros and I scroll down, I'll see all of the macros that are available on the toolbox. Those show up with a globe icon. All the ones that are enabled locally show up with the little computer icon. So here is extract soup can wrapper, but more importantly, here is soup can wrapper over radius range. So when I select this, I now see all of the, I see this option and it has already been uploaded to the Infinite Toolbox. So this you can download and use on your own. Now that invokes the source code for the menu item. You can find the menu item, so that's sort of a dependency of the macro. You can find the menu item. There are many menu items here, and if you'll find extract cylinder side from structured grid. So you can see that this is on my local computer and also on the Infinite Toolbox. So this menu item will let you take any cylinder and any image or ROI, and it will extract out the values of the image or ROI where they intersect with the wall of the cylinder. So this was programmed by Nicolas Pichet back, I think, in week 2 or 3 of the webinar series when someone asked for it. So this is available. You can just click Install for all users, and you'll have it downloaded and installed on your system. If you want to see the source code, let me pull that up for just a moment. Let's see. Can I? Give me just a moment. I'll open up my PyCharm on my system, and we'll look at the source code. So for anyone who wants to see that, give me just a moment. All right, and I see now that captions have not been visible because things keep hiding my captions. We try. All right. So here is the source code from Nicola. So this is the code where we're actually looking at a cylinder and we're looking at an image, and there is the math for computing the pixel size and computing the sampling. So here's all of your fun geometry of extracting out the data. He's actually written the method twice, I think once for an ROI and once for an image channel, but you can come in here and look at the source code, because once you download this from the Infinite Toolbox, you'll have all of this source code installed on your system in your menu items folder. All right, that's actually everything, almost everything I wanted to show you for today. I'm going to open up my my organizer again, and I'm going to grab Unwrapped. So I made the cylinder full height for this entire sandpack data, and then I unwrapped it, I think, over a radius range of 1 to 4 millimeters. It took, a long time on my computer, maybe 20 to 45 minutes. I didn't time it, but it took a while because it's not super fast and it's a bigger data set and it's a taller cylinder, but I did do it offline so that we could look at it now. So here we are at high radius, unwrapped at the 4 millimeter radius, and here we are at the 1 millimeter radius. And so that's pretty much what this data set looks like. We could go higher radius and see, what the differences are on the surface. If you have an object that's not perfectly cylindrical, then you'll see the presence of divots or protrusions, and they'll become quite clear in this inspection scenario. So that is it for this lesson. I am going to switch over and see if you guys have any questions, and we'll take questions and answers at this time. All right. I do have a question. The question is, it is interesting to know how to do SEM processing, such as removing curtaining before reconstruction in fib tomography. Well, that's a great question, and What we can do in future lessons, I mentioned that we'll probably have lessons on application topics such as poor network modeling, bone analysis, maybe some industrial inspection scenarios. What we'll do for one of those will be processing FIBSEM data or maybe processing bio-EM data, because I know there's a lot of tools and tricks that we've learned that you need to put together to apply to bio data, such as correcting charging and correcting curtaining. So I think we talked about correcting curtaining once in the image processing week. Maybe not, but in the image processing toolbox, there is a tool called vertical destripe or vertical stripe removal, and that's useful for curtaining correction. Of course, you could proceed to segment the data with deep learning and just ignore the curtains. If you paint examples for the training data and some include curtains and some do not, then the deep learning model will proceed fine and you don't even have to worry about correcting the curtaining. But I think on a bio-EM series, we'll talk about segmentation and charging and a number of different artifacts and how to deal with them in that application demo. All right, I'm glad you guys liked this demo. All right, just getting some positive encouragement here. All right, here's a question: does this macro work only in 4.1 or only in version 2020? That's a great question. I'm 90% confident it'll work in 4.1, so you should be able to download it and use it in 4.1. The menu item was programmed and validated in 4.1. The macro builder I wrote yesterday, and I wrote it in 2020, but I'm pretty sure there's nothing in there that depends on any 2020 enhancements. Next question: this tool is immediately useful and is secondarily a jumping off point for integrating the tool I'm working on. Thank you. All right, Matt, thanks for your help. Actually, you know what? I want to talk a little bit more. I had mentioned, so in this lesson, we talked about this, which is kind of a hack or a kludge. It is a way of connecting a cylinder object to a data set. I think what we should do as a proper solution, and I appreciate any feedback on this, a proper solution would probably be whenever you have a cylinder object to be able to right click on the cylinder object and then prop open a new view, which would allow you to change the radius and you would have the new view updated in real time. And so you could see exactly what is the linkage of your new view interactively to this radius. So in your other view, if you increase the radius and dragged it up and down, this would change, and that would give you a live connected view. And then from that view, if you wanted to extract out a range and create a new three-dimensional channel that had persistence. So this could be a new live view widget, was something we could engineer. The other question is, how do people want to inspect this? When I created this data set, we see that I use a constant pixel size, which means at this view, the horizontal extent is smaller than it is at this view. We could have a solution here where we keep the horizontal and not as a constant pixel size, but as a 0 to 360 degrees. So this could be a theta parameter where the x-axis is theta and the z-axis is radius. Or you could have as an option. Furthermore, the cylinder object, you may want it, if this makes sense, you may want it so that you can rotate the cylinder, and then your image's origin, or maybe we might use the word phase, would offset. So you could imagine this image translating, and where as I move the cylinder's radius, the pixels on this side pop up over on this side. I think that's probably the proper way to integrate this if we want to make this tool really useful. This is, as I say, just a kludge, but it could be useful in helping some of you with your workflows. But I would like any feedback. Just send it to we should have a feature request email list, but you can just send it to support@theobjects.com or email it to me if you want to initiate that discussion. Let me go back over to the questions and answers. So let's see what we have next. Is this the final webinar, or will there be more webinars coming next week? So there are no more webinars coming next week. The Dragonfly Wizard needs a break, I guess. What we're going to do is set up some webinars on application topics such as poor network modeling and powder analysis, maybe confocal microscopy workflows, and build those out as a longer webinar and do those once every 2 to 3 weeks. Then we will also, in sometime this summer, start some longer webinars, probably put together a 10 webinar series on programming extensions for Dragonfly, because I think there's still a lot of demand on how to support that. And then, if I can get approval, next year we'll do an image processing for scientific imaging, which is everything about what digital images are and what you need to know to use either Dragonfly or ImageJ or anything else out there. So just the general image processing topics. And in that webinar series, I also hope to discuss the imaging physics of confocal versus wide field microscopy, of X-ray CT attenuation and electron microscopy, maybe even go into atom probe tomography or EBSD and EDS. I think it's useful for people who are doing scientific imaging to be able to understand the physics of the sensors and the physics of the bombardment of your sample with radiation and what's happening, and put that all in the context of image processing. So that's something I would like to do. All right, thank you for your positive feedback. Here's a question. Sydney asks, what about Huff transforms? Do you have anything prepared for that? No, we don't. That's a great question, and there are some times, and that's absolutely something that has to be covered in an image processing course. It's just something we've never put in Dragonfly. For those of you that don't know what Huff transforms are, they are a mechanism of detecting and identifying the position of features in your image. Specifically, line features and circle features are the Huff transforms I know about. They can be computationally slow, but they can be very good at identifying circles. So if you had an SEM micrograph of a bunch of powder grains, you might evaluate a Huff transform, and those spherical grains, which show up as circles in an SEM image, would help you identify the position of them. And you can build it out so you're filtering based on radius. And it's also very good at detecting incomplete circles and incomplete lines. So I don't have any lecture material on Huff transforms, but tell us how you would want to use it in Dragonfly, because it's something we almost never hear a request from. It's been 4 or 5 years since some users I can think of right now were looking at CT images and possibly electron-micrograph images of electronic components. And of course they wanted to identify where the traces are and maybe where some circular solder joins are, and circle and line detections would be good for that. But generally in scientific imaging I don't hear much request for it, but I'd like to hear how you would like to use it. Next, Dragonfly Daily has been a great resource during lockdown. Thank you for your heroic efforts. Well, I don't know if it's heroic, but it can be exhausting sometimes figuring out what to talk about the next day. But thank you for your appreciation. All right, we've hit the bottom of our questions and answers, so thank you all for your attention and during this series and your attention today. Go and check out the Infinite Toolbox for those extensions, and grab Dragonfly 2020.1 if you don't already have it, and look for the announcement of the production release any day now. And thank you for your attention, and as I mentioned at the very, very beginning, maybe before we started recording, we will just use email campaigns to announce the next webinar series when they come out. So, thank you again for your attention. Look for future webinars from Dragonfly. Subscribe to the YouTube channel so that you know when new content gets posted, and that'll be one of the best notification mechanisms. All right, everyone. Thanks for your attention. Thanks for your participation. Everyone stay healthy, and good luck getting back to work and getting productive again. And take care, everybody.